One thing that I do want to, we need to yield here, do want to share with you that cProfile does not do is remember the events that I told you about that it hooks into. Taps into function calls and it taps into function returns. And so if I run this program, well, you can see that I've only captured the total time it took to execute G. G is a generator here. Wouldn't it be useful to capture how long each step of G took? But then that doesn't really fit well with the call style here, right? It's hard to parse apart these yields, which actually don't bubble up events to this level of the API, right? Function calls, function returns, not yields. And so if you're working with things like generators, if you're working with things like threading or asynchronously, using cProfile, it will give you some beneficial results, some results that you can look at and parse through and make sense of after some time, but it's not going to be as useful out of the box as just running some cProfile right on your very constant Python code or on your very, I want to say static, but on your Python code, right, that's not going to be using generators and all it's going to be doing single core, single thread computations. So we have timeit, which runs right a lot, or the same module or same script, I should say, or the same arbitrary Python code in a loop multiple times. It gives you the mean or it gives you the best time actually of all of those times that it runs. Now this is slightly different from statistical profiling, and what we've talked about so far, we're using cProfile. This is deterministic profiling. All that means is cProfile is actually, right, it's tapping into the Python runtime and it's just adding a little bit of overhead for every single function call. Note, a little bit of an overhead. We already know that Python function calls are slow, so is adding that extra overhead of the cProfile module going to be a lot? It's not going to be a lot in regards to, right, how slow Python already is. So if you're concerned about this impacting performance, yes, that is the answer, dead stop. Using cProfile on your script will impact its performance. You're there to measure its performance. And actually, there's an interesting aspect of cProfile. There is a parameter you can pass that will actually shave off, right, X number of seconds per function call in order to try and, right, make an adjustment to get what the timings would look like if you had not been using cProfile at all. But of course, the overhead, these small little costs are just going to vary from machine to machine and from Python version to Python version. So it's hard to pick a value that's appropriate for all Python runtimes and all different hardwares. So that is deterministic profiling, meaning we're looking at every single function call, we're timing it, and then we're reporting statistics on it, as you can see here at the bottom of my screen. How does this differ from statistical profiling though? Well, statistical profilers are things like PySpy and Scalene. If you're not familiar with these programs, they are very neat. They're used, at least PySpy is used to actually assess how, or the timings of various parts of your program if you're running it in production. You can actually launch a Python process. Say you have, oh, this is a great example. Say you have a fast API server. Am I going to run cProfile on my fast API server and just permanently having it running under cProfile? Probably not, because if I'm talking about small little costs of overhead, if I'm running a web server and it's serving a large volume of traffic, I want every bit of speed, every bit of power that I can get my hands on. And you start to lose out with that when you're hooking into every single Python level function call. What PySpy allows you to do is PySpy doesn't hook into Python function calls. Since it's a statistical profiler, it simply pulls the Python process, the ongoing Python process. You can pass this a PID, right, a process ID of an ongoing Python process, and it'll simply examine it, and it'll try its best to observe, okay, what function or where is the Python stack or current frame, I should say. And the idea here is that if it checks on that Python process a number of times, say 1,000 times over the course of a few minutes, where your program is going to be spending the most time is where is that frame that you're going to see most often. And that's why this is statistical. It's not deterministic because we're not timing every single piece of code that's being executed. We're simply checking in on the Python process once every so often. And then after we check on it X number of times, we can start making statistical estimations about how long each part of our code is taking. Now, if your program doesn't run for long enough, it's not going to have enough time to kind of check every frame, or it's not going to encounter every frame, I should say. So you do need kind of a minimum number of samples or a minimum runtime to let these programs sample for long enough. But they are very useful tools because they add even less overhead than something like cProfile, and they still give you a good gut feeling about how your program's doing. Scalene also will give you information about memory usage, which is very nice to have, especially when you're working with tools like pandas that really suck up a lot of memory. But I want to share with you one other example. And I have here just a couple of different ways of sorting things, and I'm going to time them for you. So I have my tim sort, right, which is the regular sorted function in Python. I have a bubble sort and I have a merge sort. I'm going to run this. This does take a little bit of time to run, but we're going to examine some of these outputs here, or how long each of these functions took to actually run. And I'm using timeit, and so we might need to pass numbers equals 1 here to actually get this to complete. But I will give it just a moment because this does take a minute. Okay, and there's our output. So what we can see here is, wow, the sorted, that's just so fast, right? It's 0.3 seconds. That bubble sort, oof, and that merge sort, those might be just horrible implementations. Or it's the fact that I implemented both bubble sort and merge sort while the algorithms won't be what the tim sort uses every time. But those are implemented just in pure Python. And this gets a little bit more into that theory. You can tell I'm very itching to get to the theory. We need to make sure that we compare apples to apples when we start timing things. You can see I'm not here comparing apples to apples. I'm comparing, right, something that's written in C to Python functions that are operating on Python objects using Python iteration loops or Python iteration. And so there's a no-brainer, right, that the sorted is going to be faster than both of these implementations. And you can think, if you know anything about these algorithms, that depending on how many values are actually being sorted here, these numbers will also vary widely, and we can actually see a flip, right, between our merge sort and our bubble sort. But that's about it for timing just Python code. What if we want to actually time something more? Well, we can use the time command built into, right, your Unix operating system. You can use the time command to actually measure how long something will run. And this will just run it once, right? It's not like timeit where it's running things multiple times. But what I like to use a little bit more than time is actually hyperfine. And what hyperfine will do, it's actually, you can think of it like a program level timeit. It's running this multiple times, and then it reports to me, right, the mean plus the standard deviation, and it also reports to me, right, the minimum and maximum while guessing, right, how many runs it should be performing. So this is quite useful information to know. I can tell that my sleep for 0.1 seconds, right, had a range around 0.1 seconds, and it averaged just over 0.1. What else I like about hyperfine is that you can actually perform multiple benchmarks. So here I'm just using something silly like sleep for 2.2 seconds versus sleep for 0.1 seconds. But what you would typically do is you would compare, right, the same program maybe with different inputs. Or maybe you would be comparing two different programs. Maybe I want to compare something written in pandas versus something written in polars. So you can do that using hyperfine, and it will give you, right, some nice little summary statistics about both those benchmarks and even a summary, which is just convenient to look at. A few things that are important to note here about using these tools is we're going to inadvertently time how long it takes for the Python process to start up. And so when I use hyperfine, right, on this Python program that's just executing 1 + 1, well, we're actually timing how long does Python take to start, and then how long does it take to actually execute the code. Now, this can be very useful if you're interested in that program level information, but we should be sure that we know exactly what we're measuring when we are measuring it. And so you can see here, right, these are useful. Say you have a lot of shell scripts, or say you have a shell script written in Python 3.12 versus 3.11. You can use tools like Hyperfind because you actually want to integrate, right, that program startup instead of just the execution of the code. This doesn't make sense if we're running, say, a process that never terminates. Say I'm running a fast API server. Well, I'm not going to run Hyperfind or time against it because that thing never exits unless something very bad happens in my program or if I kill it manually. And so time or Hyperfind don't make sense there. That's when we need to go into the program, right? Use something like time it within our program. There's also perf, and perf is a very low-level performance measurement. It captures things like how many CPU cycles have occurred, how many instructions were consumed since the last poll, and right, branch predictions or branch misses, cache misses, things like that. Not very useful at the Python level, right? This is useful for much lower level languages where we actually have control over, right, a lot of these things. I don't think when we're writing Python, we're thinking about cache misses. And even if you did perf it and you got something meaningful out, it's going to be like cProfile. There's going to be so much output. But if you got something meaningful out, chances are it's very hard to figure out from that output what you need to change at the Python level to actually make an effective change there. So perf is useful, right? Lower level languages. Say I'm writing some C that I then load into Python or access from a Python-based API. Well, I can perf that C code very well, and then once I get it to a spot where I'm happy with it, then I go ahead and lift it into Python. That's a useful application of perf for Python, but it's indirect, right? And then we already talked about our statistical profilers, PySpy and Scalene. Let's go ahead and talk about some of the theory here. When we talk about timing, we want to think in terms of experimental design. And this is a quote, and I absolutely love this quote. In the absence of statistical sophistication, your performance measurements could just be giving you garbage that you can put on Twitter or in a PowerPoint presentation. I'm sure you've all seen lots of graphs of micro benchmarks, and I'm not going to say they're all useless, right? Micro benchmarks can be useful for making decisions on X, Y, or Z. Which program, which library do I use? When do I use it? But there are a lot of grains of salt there, and let's go ahead and talk about some of them. I'm going to be comparing pandas and polars here. Let's go ahead and look at this graph comparing a group by operation of pandas and polars. Now, in the absence of me actually showing you in great detail what the code is doing, the first thing you need to watch out for benchmarks is you don't know what code I ran. If I don't share that with you, the benchmark is absolutely meaningless. That's phase one for take it with a grain of salt. Step two is if you're able to see the code and you can say, okay, those codes look pretty equivalent, then what you want to be looking for, right, is the timings, right, how long each thing took to make. I'll show you different ways that micro benchmarks can be misleading, but I'd say this is a decent starting point. What I've done is I performed a group by operation at different cardinalities and different group sizes, so I'm trying to cover my bases about where this program might change. I hate it when I see micro benchmarks and it's just like, ooh, pandas read CSV was slower than, oh, this is a big one. I saw a blog post about this. Pandas read CSV was slower than Dask's lazy read CSV. And in the article, they did not call compute on their Dask operation. Therefore, they never actually loaded the CSV file into memory. And you can think this is not the comparison that we want to be making. So that's why it's important to always look at the code. The next thing that you'll want to do is always get more than one measurement. We have for loops for a reason. We can get multiple measurements and we can test how robust are these things, just like time it does, just like Hyperfind does. And so when we're talking micro benchmarks, I see bar charts of just single measurements. How reliable is that measurement? You can think that your computer is going to be your machines under different amounts of stress at any given moment, and so it makes sense to measure something multiple times to make sure that it is reliable. And so that's what we'll do just here in our next example. But what these one-off measurements, or if I run multiple measurements and then aggregate back down, there are a lot of statistical assumptions that we're making. First is the assumption of normality. Timings from a computer are not going to be normally distributed. Especially with all the factors that might be varying that can affect those, I don't think the central limit theorem is going to uphold very strongly for us, and so maybe the mean is not the best choice of thing to report. However, I will say this, the mean does give us a useful reference point. Is it as statistically rigorous or interesting as an actual statistical test? No. But do we need to be running statistical tests to make kind of eyeball-based judgments? Not necessarily. The next thing, comparing distributions, we just talked about this. You want to run something multiple times, collect multiple observations, and then compare all of those observations to each other. The last thing is the asymptotic discussion. All this refers to is the fact that programs will have various timings depending on how they're being run. And you can see I tried to tap into that in the previous example with things like our cardinality and our group size. I tried to find factors that would affect our timings and actually might cause shifts or differences down the line, but it's very hard to say that this is exhaustive and that this is actually approaching what the timing will be under some criteria.